Hello everybody, welcome to week 1 and video 3 where we move into graded potentials and action potentials. So in the last video we talked about the resting potential and how mostly potassium permeability drives the cell membrane potential down to -68 or so. This video is going to focus on how events at the synapse in the dendrites can generate graded potentials that then may or may not trigger an action potential. So we're going to talk about stimulus strength and graded potentials, and then what triggers an action potential, which ions are responsible for each phase of the action potentials, and how action potentials travel down the axon so quickly and in the right direction. Okay, so we know that obviously the cell is not always at rest. So in this brain, you can see all the lit up areas that are representing neurons firing action potentials. And what that is essentially just a surge of ions moving across the membranes of the neuron and traveling down and then being translated into a chemical signal at the synapse. So two things need to occur for this to happen. First, you have to have an increased permeability to sodium. And this is where we're in the receiving cell in the dendrite. And so this is achieved by mostly ligand-gated sodium channels that open in response to a neurotransmitter signal. This causes a graded potential in the neuron. And if that graded potential elevates the membrane potential of the cell to a threshold level at the axon hillock, then you get an action potential. And the critical threshold is usually around -55 millivolts, at which point the positive charge, the more positive charge, right? You're going from -68 at rest to -55 at critical threshold. And then once that happens, the voltage gates on voltage-gated sodium channels open, and this really increases the permeability to sodium. And so sodium, along its really strong driving force, floods the cell, drives that big peak of membrane potential in the action potential, and that causes the next voltage gates a little further along the axon to open, and it zips down the axon. So let's look at that more closely. Maybe. can't get the screen to, there we go. Okay, so here's a picture of showing an axon terminal and a synapse. And the presynaptic neuron has a released neurotransmitter that has caused this ligand-gated sodium channel to open on the postsynaptic neuron's membrane. And what it's showing is that there's a physical place where that presynaptic cell synapses onto the postsynaptic cell. And that physical place along the membrane is where channels will open in response to that neurotransmitter. So sodium starts to flood locally across the membrane, down its gradient, its concentration gradient, and it starts to flood the postsynaptic cell. And what this is showing is that physical space matters, where in the cell this opens, how long it opens, how many different channels open. All of those things matter for reaching threshold or not. Because as you can see in the picture, you have kind of a hot zone of sodium right around the ligand-gated channel. And then as that sodium diffuses across the cell, down the concentration gradient, you get a weaker signal. And that's because that sodium is diffusing across space, and it's moving in all directions, and it's moving down its concentration gradient. So the graded potentials reflect those aspects. So they're going to reflect how strong the stimulus was. In other words, how much neurotransmitter is released, which largely reflects how many times that presynaptic neuron is firing and releasing neurotransmitter. So you have a local current flow that's kind of a wave of depolarization that moves through the cell, and that loses strengths as it dissipates throughout the cell, as I mentioned before. And also as some of the sodium, actually, I'm going to go back one. Some of the sodium is lost out leaky channels, which is represented by this here. Okay, so there's some sodium that is lost. Other sodium might interact with other things that are in the cytoplasm, things like chloride ions. They may bind together, essentially neutralizing that sodium, or it may interact with other molecules that reduce the signals, reduce the sodium signal. That's called cytoplasmic resistance. Basically, the sodium is just kind of captured and interacted, bound up with other chemicals, and so it doesn't reach the trigger zone. But if they're strong enough, then a graded potential that reaches the trigger zone will open those first voltage-gated sodium channels. So let's look at that. This is an example of a graded potential that's not strong enough to trigger an action potential. And what you see in this picture is, again, you have a presynaptic neuron that's releasing neurotransmitter and causing a graded potential, a graded depolarization. So the neurotransmitter binds, sodium channels open, and a certain amount of sodium floods the cell and depolarizes it. That's this here. So that kind of upshoot. If you go a little further away, of course, it takes a little more time for the sodium to diffuse that far. And you already see a reduction in how much sodium makes it that far. And this is, again, because of cytoplasmic resistance or because of leaky sodium channels and the loss of sodium back out of the cell. And by the time you get all the way across the cell to the trigger zone, you're below the threshold that is required to open the voltage-gated sodium channels. So right here, the trigger zone is defined by the presence of voltage-gated sodium channels. That's what makes it the trigger zone. It's the first place in the axon, and it's right at the start of the axon, where you find voltage-gated channels. And so all along the dendrites, back up here, these are ligand-gated sodium channels. So those require neurotransmitters to open. But the red ones at the trigger zone, those represent voltage-gated channels. And so all you have to have is at least negative 55 millivolts or higher, more positive, to open that voltage gate and cause sodium ions to flow. So until you get to negative 55 at the axon hillock, you don't get an action potential. So in this example, there wasn't an action potential. In this example, there is. So presumably there's more neurotransmitter, either by repeated stimulations or multiple axons, multiple presynaptic cells releasing neurotransmitter, so you get a stronger graded potential. And that graded potential in this case, by the time you get to the axon hillock at the trigger zone down here, where there's voltage-gated channels, I'm doing a lot of this in red here. There you go. The graded potential is above negative 55, and so it triggers open, it pushes open the voltage gate, and sodium flows in, and it flows in such high amounts that it will trigger the next set of voltage gates that are a little further along the axon, and down it zips, down the axon. The conduction of an action potential is basically just the opening of sodium gates, like a zipper, down the axon until it reaches the terminal. And this is an all or none event. Okay, there's enough voltage-gated sodium channels arranged along an axon to always reach threshold for the next set of voltage gates. Right, so you have an axon. I'm going to draw it like this, because if you remember, we'll say that's the end. if you remember, axons are myelinated, right? So big sections of the axon are Schwann cells wrap around the axon in order to insulate it and not allow sodium permeability in that section. But these nodes of Ranvier in between those myelin sheaths, those are where you get the voltage gated sodium channels. And that's where sodium can flow into the axon. And enough sodium goes in this voltage gate when it opens to ensure that the next one, that the sodium reaches the next voltage gate and opens it. And then you get more sodium and it propagates down like that. If those nodes of Ranvier were too far apart, so you got too much dissipation because of cytoplasmic resistance, then you would have a problem with conductance, right? The signal wouldn't propagate, and that would be a big problem. And there are some disease states where you see that. Okay, so I'm going to draw as a review an action potential. This may take 2 slides, which is why I created 2 slides there. And I'm going to first draw what an action potential looks like, and then we'll talk about the phases. So this is the membrane potential here, and here's -90, so that's the equilibrium potential for potassium, and we'll have it go up to +55, the equilibrium potential for sodium, and these are going to be millivolts. And then we have rest, -65 here, and then I'm going to draw a dotted line to represent threshold. So that's where the voltage gates would be triggered to open. So what we see is, I'm going to draw some numbers here that will correspond. So 1 there, we'll look at my notes, 2, 3, 4, 5, 6, and 7. Okay, and then we'll just label this as threshold, critical threshold. Okay, so we're going to start with number 1. So at event number 1 is basically the ligand gated sodium channels open. Okay, the ligand gating sodium channel opens, and we'll just do some little drawings here. So that's a receptor amongst, worked in, whatever, located in the membrane. And what you need is neurotransmitter. So some kind of stimulatory neurotransmitter from the presynaptic cell binds to that receptor, and so doing opens the channel so that you can get sodium flow into the cell. And this causes the membrane potential to start to increase. Okay, so it's depolarizing. And it's going from the 1 to the 2, where you start to see an increase in the membrane potential. So at 2, this is where we've reached critical threshold. So these graded potentials reach critical threshold, critical threshold at the axon hillock. If it hadn't, then you would just see it drop back down to rest. But it reaches the critical threshold, which means that the voltage gated sodium channels open. So these little guys, I'm going to draw our channel here in the membrane again. And normally these sit with a gate blocking sodium from entering the cell. But when you reach threshold, that gate pops open, okay, it's repelled. When you reach threshold, that means that sodium from the graded potential from the ligand gated channels are diffusing closer and closer to the axon hillock. When they reach the axon hillock, there's all this positive charge starting to build. It's still negative 55. It's not like it's that positive, but it's positive enough that this gate swings open, and that's going to allow more sodium. I'm going to draw it in orange here. So more sodium then floods the cell, and now you get just a huge influx. And this is going to be the action potential that's going to go trigger the next set of voltage gates at the next node of RANVA. Okay, so now this is where you're entering into that really big peak. Okay, so as this process happens, we're in 3, where we have really high permeability to sodium. And VM starts to approach sodium's equilibrium potential. So this plus 55 millivolts. Okay, so boom, voltage gates open and sodium starts to really increase. What happens at 4 is that the voltage gated sodium channels deactivate. Basically how that happens, here's your voltage gated sodium channel. And there's a portion of the protein of this channel that's positively charged. And as you get this buildup of sodium that's come in from itself, right? This is, the sodium has come in and it's building up, it's building up, it's building up, it's building up around this channel. And eventually that's enough positive charge to push this positive section of the sodium channel in to block it. And now sodium can no longer enter, okay? It's lost its ability to come into the cell. That's the first part that stops the VM from increasing any further. The second part is that there are voltage gated potassium channels that open. These are essentially on a delay. So they're triggered fairly early in this action potential process, but there's a delay as to how quickly they open. But once they do, then potassium ions, which are positively charged, are going to move out. As the positively charged cations move out, and remember, now they have a really strong driving force because inside the cell is now plus 55 because of all this sodium that came into the cell. And so now potassium really wants to get out of the cell because it likes it at negative 90 millivolts. And so it'll have a really strong driving force to get out of there. And that's where we get to number 5. So we have really high permeability to potassium. VM drops and moves towards the equilibrium potential of potassium, which is negative 90 millivolts. And in fact, as the permeability for sodium closes, as the channels deactivate, and the permeability for potassium opens as all of those voltage gated potassium channels open, then you get, this leads to 6, which is a period of hyperpolarization. And it's called the overshoot, where there's a moment in time where there's so much potassium permeability and so little sodium permeability that you get even closer to potassium's equilibrium than is normal at rest. Okay, and so then the last step here, I guess we're not going to need a second page, is that all of those channels will reset. So as the cell becomes more negative, I'm going to draw this in purple. The channels reset. In other words, this gate closes, the inactivation gates open. So they're still closed because this other gate is closed, but everything basically resets. That gate closes all during this kind of restoration to the resting state. So this hyperpolarization period where it gets to be -90 or close to it is what's going to pull all of those things back into their resting state. And now we are left to the point where the sodium potassium pumps have to do their job to restore the concentrations to normal. And one note about that, it's not that the entire cell's concentration changes necessarily, but right there at the membrane, this is happening super fast and locally. And so you get these pumps that are on the membrane that are going to pump sodium back out of the cell and pump potassium back into the cell and restore the concentration gradients. Okay, so as soon as I move off this screen, that's going to all go away, but it's in the video, so there you go. Okay, so there's our action potential. And one thing that's interesting is when a section of axon depolarizes, there's nothing to prevent sodium from flowing in both directions along the axon. And so one question you might wonder is, how does the signal travel in the right direction? In other words, towards the presynaptic membrane at the axon terminal. And that goes back to these kind of refractory states for the channels, for the voltage gated channels. So in this next picture, we'll see that there's the trigger zone that's turning yellow because the voltage gates are open. So sodium's flooding the cell, and you're starting to see the signal propagate down the axon. And so that yellow region is getting larger as the positive charge flows. But then there's this represented schematically by purple zone that is the refractory zone. And essentially, this movement of potassium, which is on a delay. So remember, the voltage gates for the sodium channels open first, and that's where you get that yellow positive flow. And then after a slight delay, the potassium channels open. And so it's impossible for the sodium channels to reopen again because there's so much potassium permeability that it can't. And so you requires that hyperpolarization, that overshoot, in order to reset the sodium gates anyway. So there's going to be a period of time where that section of axon cannot propagate another action potential. It has to have enough time to reset those voltage gates in order to fire again. And so that essentially creates a situation where the action potential can only zip down the axon in one direction. Okay, so finally, I'll just end on this, that the speed of the action potential is dependent on properties of the axon. So the larger the axon, the faster, and that has to do with conduction and essentially surface area, but also conduction speed or velocity is dependent on the resistance that's found inside of the cell. So as sodium ions go into the cell, remember they can interact with things inside of the cell that slow down the spread of those sodium ions. And one way to make, and then we get leaky channels where you get loss of sodium ions. And one way to make that conduction velocity faster, as I already mentioned, is to myelinate the axons. And so that's where those Schwann cells wrap around and prevent the loss of sodium, except for at the nodes of Ranvier, where the movement of sodium ions except for at the nodes of RANVA. And so what that effectively does is it makes the signal jump from node to node, and that increases the conduction velocity. Okay, so hopefully that gets you guys up to speed on action potentials. And there's gonna be one more review video before we move on to our first topic.